Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to talk about equilibrium and the Haber process. We're going to start off by reminding ourselves about the chemistry behind the Haber process for the production of ammonia. We're then going to look at, in terms of how we conduct this process, this balance between reaction rate and yield. We're then going to look at the effect of yield relating to temperature. We're going to look at yield relating to the pressure of the system. And then we're going to look at the role of the catalyst in the production of ammonia. And ultimately then we're going to synthesize this together to think about the nature of what we call compromise conditions. Once we weigh up all of these factors, how do we decide what's the best way forward? So the Haber process is the production of ammonia, or NH3, from nitrogen and hydrogen gases. So we see the chemical equation here. It's an exothermic process. It's an equilibrium. And it has an equilibrium constant at 300 degrees Celsius of 4.34 times 10 to the minus 3. So it lies significantly to the left-hand side of this equation. That is, we don't get a very high yield of ammonia from this particular process. So what do we mean when we're talking about yield? We think about how much product is formed. How many moles of product would we actually obtain? How many litres of liquid, or litres of cubic metres of gas, or whatever that might be. And then when we think about reaction rate, we're now then thinking, as it hopefully would be obvious to you, how quickly that product is formed. So not how much you get, but how quickly you get it. So we measure it typically in moles per litre per second, or some unit of time, maybe minutes or hours or things like that, depending on the speed of the processes that we're concerned with. But at an industrial scale, we're typically thinking about fast processes. So how many moles per litre do we get for every second that reaction is taking place? So it's important that we kind of have a good concept in our mind about what these two terms refer to, because we're going to be addressing both of them in a range of different factors as we go through from here. So, but first we're going to now think about the role of temperature in terms of how much ammonia that we get. Now, I mentioned earlier that it's an exothermic process and it's an equilibrium reaction. And so what we can consider here is saying, all right, well, what happens to the amount or the percentage of ammonia that we get at various combinations of pressure and temperature? Okay, so in increasing temperatures and increasing pressures. 1 atmosphere is atmospheric pressure. Okay, so you can see, 1,000 times atmospheric pressure all the way up here. And then we've measured the percentage yield at various kind of conditions here. Okay, so now we can see, if we look at it here, that the highest yield that we get is down in this corner of the table at relatively low temperatures and really, really high pressures. But that as we either decrease the pressure or increase the temperature, that our yield decreases significantly. Okay, all the way from close to 100% up in this area, all the way down to 0.2% in this corner at low pressure but very high temperature. So what we can see is that we're going to have to be very careful in terms of how we make our choices about the conditions that we pick so that we can maximize the yield, but we have to kind of pick what's the right point. And that's something that we need to look carefully at Le Chatelier's principle of this equilibrium to help us make a choice. So one of the things we identified is that the highest yield we get is at the lowest temperatures. And Le Chatelier's principle helps to explain this, because the forward reaction is exothermic. At low temperatures, that is where energy has been removed from the system, that it's going to shift to the right-hand side to replace that lost energy that's been transferred out. And so that favours our forward reaction to produce more ammonia. The problem that we have, though, is that the rate of production is highest at high temperatures. Now that comes back to collision theory, that idea that we have the greatest kinetic energy at these temperatures, so we get more frequent and more successful particle collisions. But this means, from the equilibrium point of view, we get the lowest yield because we're favouring the endothermic reverse reaction. We get less ammonia, not more. So we may get things faster, but what we're actually getting at the end is a much smaller quantity. Whereas here, at low temperatures, we would get a greater amount, a greater yield, but at a very low rate by comparison. So what we have to do is we have to pick the best balance and say, right, well, let's pick a moderate temperature, so we get a better balance of rate and yield. But then what about thinking about pressure? Saying, all right, well, we saw that pressure had an effect on yield as well, that high pressure gives us more ammonia. Now, part of the reason for that, the higher yield at higher pressure, is that the forward reaction is again favoured, but this time because we have 4 particles of gas on the left versus 2 particles on the right hand side. So you can see here we've got 4 particles total on the left, 2 particles total on the right, so an increase in pressure is going to favour shifting to the right hand side to try and reduce that pressure. But higher pressure has its own downsides, that is, high cost and high risk. So it's not so much in terms of a rate factor, but in terms of the actual the logistics of setting up this process in an industrial scale. That this sort of equipment is very expensive, very difficult to maintain because of the high pressures that are needed to get this working. There's a high risk of explosion or catastrophic failure because you're trying to maintain temperatures much greater than the atmosphere around the plant. And so then the potential for dramatic failure is significant. Now, it may be highly uncommon if you've planned for it carefully, but the actual outcome would be catastrophic. And so it's important for us to recognise that this is not without downside. But if we take the same sort of principle that we did before and say, all right, well, how about a moderate pressure? So we get the best balance of yield versus practicality, that is cost and risk. Okay, because there's not a great deal of point setting up a plant like this if it's going to be extremely expensive and extremely dangerous. You've got to get people to work there. You've got to be able to actually ensure a safe working environment, as well as then the impact on the community as well, making sure that there's no chance that ammonia gas, for example, is going to leak into the atmosphere because of a failure. Okay, so it's important to consider these factors in terms of setting up this process. Another thing that's going to influence how this process happens is the role of a catalyst. So we've got a bit of a diagram here to actually show how the catalyst, in this case magnetite, which has the formula of Fe3O4, how it actually facilitates this reaction when the particles of reactants are in the gas phase. So what we have is that we've got the gas phase reactants that are floating around out here, and they interact with the solid catalyst. Okay, so that as they kind of make contact and then attach onto or adsorb onto the surface of the catalyst, that then it actually helps facilitate the breaking of the covalent bonds. The atoms then on the surface can actually kind of readjust and reconnect into a new arrangement and then leave the surface. And so what that does then, by providing a binding site for those gas particles, is that it means that the energy pathway for this reaction is a lot lower. You're not relying on gas phase collisions, but rather they're actually kind of particle collisions on the surface, which is a lot easier to take place and a lot more likely to be successful. So we have a lower activation energy, which means that the required temperature to get over it actually can be a lot easier, because we're already going to have a greater proportion above the activation energy for a given temperature, because the catalyst is doing the work for us. So if we want to produce ammonia on an industrial scale, considering these factors of yield and rate, cost and risk, that we end up coming up with or developing some compromise conditions. So we choose a moderate temperature because that gives us the best balance of a practical rate and an effective yield. Okay, we choose a moderate pressure because that's going to give us the best balance of cost and risk versus the yield of ammonia. We're going to use the impact of the catalyst to help lower the temperature that we need in order to be as effective as possible. So we reminded ourselves about some of the chemistry of the Haber process that's involved in an equilibrium reaction. We looked at and defined reaction rate and yields so that to help contextualize what we needed to learn more about. We then looked at the effective yield and temperature. We looked at the relationship between yield and pressure. We looked at the role of a catalyst, and then we looked at how compromise conditions can be developed to help get the best balance of all of these factors in the production of ammonia. Alright, thanks very much for watching. Don't forget to like and subscribe. Bye for now.